Hello, everyone, and welcome to today's webinar, sCMOS Cameras for Quantum Imaging. I'm Cassie Saltman of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Teledyne Photometrics. To learn more, visit www.photometrics.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. I'll go ahead and highlight that now so you're aware of the location. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. I'd like to welcome our speakers, Dr. Matthew Kose-Dunn, Marketing Manager, Teledyne Photometrics, and our guest speaker, Professor Markus Gräfe, Professor for Experimental Solid-State Quantum Optics at TU Darmstadt. Matthew, you may now begin your portion of the presentation.
Hello and welcome to another Teledyne Photometrics webinar with me, Dr. Matthew Kose-Dunn. Today's webinar is all about sCMOS cameras for quantum imaging, an exciting and developing recent field of research using Hello and
My apologies, we're having some technical issues. Bear with me for just one moment.
Hello and welcome to another Teledyne Photometrics webinar with me, Dr. Matthew Kose-Dunn. Today's webinar is all about sCMOS cameras for quantum imaging, an exciting and developing recent field of research using quantum phenomena to inform current imaging techniques and even develop new, novel ways of imaging, microscopy, and spectroscopy. Firstly, a little bit about us at Teledyne Photometrics. We design and manufacture high-end cameras for scientific research. We support demanding quantitative imaging, and we're a market leader for scientific CMOS technologies. We've been around for a very long time, established in 1978, and part of the Teledyne Imaging Group since 2019. On this webinar today with me is our guest speaker, Dr. Markus Gräfe of TU Darmstadt, Germany. He's a professor of experimental solid-state quantum optics, whose research includes quantum imaging, integrated quantum photonics, and quantum source development. We'll hear more from Markus later on in the webinar. So, in order to understand the impact and possibilities within quantum imaging and quantum optics, we first need to understand the special phenomena that occur within quantum physics. While classical physics is likely very familiar, some of the core rules begin to break down or change as we get to the extremely small quantum scale. We're now dealing with quantum physics. Physics at the quantum scale is probabilistic. Strange phenomena can be observed and utilized. We're going to go through some of the major ones, but this section is not exhaustive. Quantum physics is a complex and rapidly developing area. First is superposition. This is the concept that particles can exist in all states or locations simultaneously until observed. A good way to explain this is through a more well-known application of quantum physics, which is quantum computing. So in classical computing, the basic unit of the computer is the bit, where 8 bits makes a byte. So each bit carries information and is either a 0 or a 1. The classic binary code. For quantum computing, it's a little different. So the basic unit of quantum computing is the qubit or quantum bit. This is different in that it can be a 0 or a 1 or both until it's observed. This expanded complexity of having additional states in the qubit allows quantum computing to perform operations that would be impossible for standard computers, or that would take a very long time. The architecture of the basic bit is completely different. So this results in many exciting applications of quantum computers, and they are one of the more active areas of quantum research. Modern, powerful quantum computers can use around 100 photon qubits, but can be unstable as these qubits are quite fragile and can lose their quantum properties. But the basic essence here is that the qubit is operating in a different way to the classical bit because of superposition. These qubits can exist in a 0, 1, or both state until observed, and this gives them more complexity. Another phenomena here is entanglement. This is where the waveforms of two or more particles interact and mix, becoming a single quantum object, regardless of their physical distance apart. So a good example of this is when light passes through a non-linear crystal. So a photon of light passes through a non-linear crystal and is split into two entangled photons. Here we've labeled them A and B. These entangled photons add up to the same energy as the original. So even in quantum physics, we can't generate energy out of nothing. But the two entangled photons are dependent and are able to react in predictable ways when observed. So if A spins down, in this example, B will spin up. This occurs even at a long distance. And these two particles are entangled and will react in this way. Even, researchers have used this to teleport quantum information up to 40 kilometers away. And these entangled particles still retain their entangled properties. As we will see later, this ability to entangle photons has exciting applications for imaging. Another phenomena is tunneling. In classical physics, particles that have insufficient energy cannot reach the other side of a barrier and are typically blocked or bounced off. However, if the barrier is sufficiently thin, in quantum mechanics, a particle has a chance to tunnel through the barrier to the other side. This is quantum tunneling. It occurs more easily the thinner the barrier is, and it has to do with the wave-particle duality involved in quantum physics. But essentially it means at the quantum scale, particles can sometimes pass through barriers that they would otherwise not be able to. This occurs very readily when the barrier is around 1 to 3 nanometers, for something the size of an electron at least. And this has a significant impact on things like consumer electronics, because now that transistors on the nanoscale, every year transistors get smaller and smaller in an effort to fit more and more of them on a circuit board. Now that transistors are on the nanoscale, electrons occasionally can pass right through the silicon and cause unpredictable effects. This is the reason behind something called a silicon lottery. Certain microelectronic devices such as PCB boards and CPUs, GPUs and more can have variable performance even if having the same specifications. And it even affects scientific cameras, which is why each of our cameras comes with its own certificate of performance. Things like quantum tunneling can now affect electronics and vary performance from individual camera to camera, because sometimes the electron will just go straight through something that's supposed to block it, for example. Things like wires wouldn't be very useful if the electrons would just spill out the sides all the time. But that's quantum tunneling. There's lots of other quantum phenomena, including things like superconductivity, superfluidity, phase transitions. There's much, much more. The possibilities are wild at the quantum scale. And we're at the stage where these phenomena are being applied to real-world technologies and engineered into devices with unique properties compared to their classical physics counterparts. And so this brings us to quantum imaging. Quantum imaging is one such area with exciting applications of quantum physics, but it isn't a single technique, but it's a whole field that covers many different approaches. It all consists of applying quantum phenomena to imaging, microscopy, spectroscopy. There are broadly 3 categories of quantum imaging. The first is entanglement-based quantum imaging. This is, as I described earlier, typically using entangled photon pairs by passing a photon through a nonlinear crystal. You can see from this diagram that the laser has been split by the crystal into entangled photon pairs. This idea has been around for a while. It was even described by Einstein in 1947, where he mentioned that he couldn't seriously believe in quantum theory because of something called spooky actions at a distance. These entangled photons will remain entangled even at large distance apart. And in this time, quantum physics was a crazy idea that flew in the face of established classical physics, which Einstein was quite invested in. And the idea was later given the Nobel Prize for Physics in 2022. The prize was given for experiments with entangled photons. So the concept has rapidly developed over time, and we're now at the stage where we can use this kind of quantum phenomena for established imaging purposes, which we'll show a bit later. The next is correlation-based quantum imaging. This is similar to classical correlation techniques, but often these correlations are much stronger at a quantum scale. I should note that entanglement is strictly a type of correlation, but there are also many others. So these include concepts like sub-shot noise imaging. With imaging, you're always subject to something called photon shot noise. With quantum physics, you can avoid this, in theory. So you can have two entangled or correlated photons where one interacts with the sample and the other interacts with the local noise pattern. This can reduce the effect of photon shot noise and subsequently increase the signal-to-noise ratio because you've reduced a source of noise that was otherwise very difficult to deal with. This, of course, requires a camera with a very high detection efficiency, but a lot can be gained from this kind of technique if you're able to do it reliably. Another example is squeezed light. In quantum physics, there's a concept of squeezing light to reduce its quantum noise. This is used by gravitational wave detectors like LIGO and Virgo. And there are many other applications of correlation-based imaging, but this is outside the scope of this webinar. So the last I'm going to talk about is interference-based quantum imaging, which uses the non-classical interference of wave properties and an interferometer. This kind of thing is based on the classical physics concept of wave-particle duality. So this is a quantum mechanical concept where you can fire electrons through a double slit, and on the other side, rather than getting two shadows as the electrons pass through either slit, you get 5. This is due to the electrons being treated as both a particle and a wave, and if you measure this, it collapses back into 2, and so you have the interference of these electrons as a wave, even though they're also treated as a particle, and this is the wave-particle duality. And this relies on interference between quantum particles. And you can use this for more imaging applications. The essential concept here is that these quantum imaging categories can be used in real imaging to enhance resolution and sensitivity and allow imaging that was otherwise not possible with classical physics. And this is something that's worth looking into with an example. So I deal a lot with scientific cameras. These cameras are silicon-based, and they are extremely efficient in the visible wavelength range, around 200 to 1,000. The real peak of efficiency comes from around 400 to 900, the visible light range. You can see the peak here is around 600 nanometers. So they're really excellent at working within the visible light range. However, if you want to image at UV wavelengths or near infrared or shortwave infrared or further out into the terahertz frequencies, the detection efficiency is much lower, and sometimes the wavelengths just go straight through the silicon or don't have enough energy to activate the silicon. So some wavelengths you can't image very efficiently. This is especially significant for people who want to do quite short wave infrared at 2000 nanometers. There's lots of benefits from imaging at longer wavelengths. Entanglement-based quantum imaging technologies can provide a solution to this issue. This is quantum imaging with undetected photons. You have a light source that's quite high energy, around 300 nanometers. You split this with a nonlinear crystal into 2 entangled photons. One with a very long wavelength and low energy, which interacts with the sample. At around 1,000 nanometers, photons at this infrared wavelength have less scattering and better penetration. This makes them better for imaging deeper into samples, such as this whole mouse. However, if this 1,000 nanometer wavelength photon interacted with the camera, the detection efficiency is quite low, almost too low energy to interact with the silicon. But the photon that interacts with the camera is 500 nanometers at a visible wavelength, where the camera is very efficient. Because these two photons are entangled, whatever occurs to one photon occurs to the other. You're effectively imaging the sample at 1000 nanometers and detecting the image at 500 nanometers. This gives you the best of both worlds, where you have reduced scattering and better penetration within the sample, while you're maximizing detection and efficiency and sensitivity at the camera. This is the quantum imaging with undetected photons. This kind of technique has widespread benefits and applications. Your camera is essentially able to operate at maximum efficiency regardless of the excitation wavelength. As long as the two photons add up to the same energy as the initial light source, you can use this for all sorts of applications. So by applying these quantum phenomena to industrial and research fields, new technologies and new methodologies can develop. So we're at quite an exciting stage. We're moving from quantum research to engineering these technologies with real-world applications. The potential applications of these technologies are vast, and they will revolutionize imaging, particularly microscopy, spectroscopy, and even camera development. The range of different quantum research areas and applications is vast and will only continue to increase in the future. Quantum imaging itself is a rich and nuanced subject. So to better explain these concepts that I've briefly outlined, I'd love to welcome Professor Markus Gräfe, Professor for Experimental Solid-State Quantum Optics at TU Darmstadt. His research includes quantum imaging, integrated quantum photonics, and quantum source development.
So my name is Markus Gräfe. From the background, I am a physicist. So I did my PhD in the field of integrated quantum photonics, and afterwards I started a research group at the Fraunhofer IOF in Jena with the topic of quantum enhanced imaging. So we actually consider non-classical states of light and how they can be used to establish new imaging or spectroscopy methods, or to enhance given methods in order to overcome certain classical limitations. And I mean, this is the main core. We also consider quantum hardware development, and some small projects go into the quantum communication direction. But I mean, the main focus is really on the quantum imaging and quantum spectroscopy part. Well, that's a complex question, actually. So there's not the one quantum imaging. Actually, quantum imaging is a whole field which covers many different approaches or technologies. And I think that one can categorize it in three big categories. So one type is that where you use entanglement of photon pairs. So it's like entanglement-based quantum imaging. The second field would be where you only use correlations, which you can only find in classical physics as well. But often quantum correlations become stronger and therefore have some beneficial properties. But then correlation-based quantum imaging. And last but not least, interference-based quantum imaging, where you utilize non-classical interference properties of, for example, two-photon wave functions and things like this. But at the end, I mean, there's an interferometer involved, because it's called also interference-based. I think those are the three main categories where you can all distribute the different quantum imaging techniques into these categories. And we're actually working on all three of them. But I have to admit the strongest focus lies on the last one, this interference-based quantum imaging technique. In general, all those different quantum imaging techniques have in common that they work best in the so-called low light regime. So whenever you want to have a low illumination dose on your sample, for example, it's a photosensitive sample, then quantum imaging techniques seem to be very beneficial. Yeah. Because they can give you often very good signal-to-noise ratio, even in such a low light regime. And maybe also to categorize it, this entanglement-based quantum imaging, for example, promises, or there are certain techniques, they promise a better resolution that you can normally achieve with classical light. Yeah. However, one has to admit this is still a kind of academic experiment. Yeah, I mean, there was a proof of principle already, but it could not find any way into application, because for doing this you need certain states of light, and it's super hard to generate those states of light. Yeah, there's still a limitation there. For the correlation-based imaging techniques, for example, there's something called ghost imaging. It has one big advantage: you can have so-called subshot noise imaging. Yeah? So you can take images below the shot noise level, which is a super cool thing because then you're not bound by the shot noise. You can have better signal-to-noise ratio than ever possible with classical light. The big obstacle there is that this only works well when the losses in your system are very low. Yeah, so rule of thumb: whenever the losses become larger than 50%, then this effect is more or less vanished. Yeah. Nevertheless, if you think about squeezed light, which also is based at the end on correlations, they are already used in the gravitational wave detection systems at the LIGO Virgo system and also at the GEO 600. Yeah, I mean, this is a very nice example where quantum optics or quantum physics at the end is already used for, let's say, semi-commercial applications. Yeah, I mean, this is like a standard tool now. Use such squeezed light sources in order to enhance the sensitivity of these interferometers that are there for detecting gravitational waves. And last but not least, for this interference-based imaging, there the biggest advantage actually is that you can do images in extreme spectral ranges without the need of having a camera or a detector in this extreme spectral range. Just think about the following: you want to do an image in the mid-infrared or terahertz regime because your sample is responsive in this wavelength regime, but that's actually very hard to find good detection systems, especially the cameras. All the good detector technology is in our smartphones. It's lithium-based, yeah, and this is blind above 1,000 nanometer, roughly. Yeah, so whenever you go beyond this wavelengths with longer wavelengths, it's really hard to find cost-efficient and also performance-efficient systems for detection. And there we can actually have an expedient with quantum imaging. This technique is called quantum imaging with undetected light or with undetected photons. And it allows to spectrally separate the illumination part from the detection part. So really you have two beams of light. They are quantum correlated with each other. Yeah? One beam is in the, let's say, mid-infrared. The other one is in the visible range. The mid-infrared one is good for the interaction with the sample, and the visible one is very good for the detection. And it's really the case, I send only mid-infrared light to my sample, and I send only visible light to the camera, and I still see the object in the camera. This is like spooky imaging. This is really one of the very fancy examples for this non-intuitive behavior of quantum optics, but it works astonishingly well in the laboratory. And now there are already demonstrators that can also be put outside the laboratory for this kind of technique. So there are several techniques. The most common one is really the absolutely most common one is still by so-called spontaneous parametric down conversion. This means you have a pump laser which you shine onto a nonlinear material, typically a Chi2 nonlinear crystal, yeah, like KTP or BBO. And inside you can imagine the following: there comes a pump photon, and then inside it can spontaneously decay into two daughter photons. Yeah, and this process of course needs to obey energy and momentum conservation, and therefore if you tailor this process, I mean, you have some degrees of freedom to tailor this process, you can have large energy separation between the two photons that are generated. Just add it up, they need to be the same energy as the pump photon, but I mean they can have different energies, meaning different spectral characteristics, meaning different colors or wavelengths. So mid-infrared, visible, for example. This is easily doable. And this is like a typical source that one utilizes for various quantum imaging experiments. I would say the first one, where it's about this entanglement-based imaging, that one has very different ways of doing this imaging. Often there are single photon detectors are enough to get any knowledge out. Whereas for the correlation-based quantum imaging, like ghost imaging, there you need definitely a camera that can be triggered, yeah, because you have two photons. One is on one detector, one is on the camera, and the one detector needs to trigger the camera that you make some correlated image, that you get a correlated detection event out. So you need cameras that can be triggered, or ideally have a timestamp for each pixel for each photon event. Of course, I mean, this is not easily doable. This is still far away from commercial cameras that one normally uses. So what people use there is really gated cameras where you can put a trigger signal. This works well. And as said, where we focus most in is this imaging with undetected light. And there you have the advantage you have to detect only a single photon stream, so no correlation events. And there you can use very sensitive, freely available or commercially available camera systems. So the moment you need some sophisticated devices like scientific sCMOS cameras, which come with a very low noise ratio, good readout characteristics, and of course a high detection efficiency. Because I mean you're still operating in a single photon regime, so you're in the quantum domain, and every photon counts at the end. So therefore you need, let's say, a camera which is superior in its performance. But the good thing is that they are already commercially available. When you have this correlation-based imaging, often acquiring a whole image takes several minutes. So it's actually quite slow. Whereas actually for the imaging with this undetected light, you can have up to video rate imaging properties. So we can go to 20 milliseconds, maybe even lower with the acquisition rate. I think this is easily doable for most of the camera systems. I think the super high speed is not that necessary. I think it's really the benefits that we see from the systems that we are using. It's really the good detection efficiency, the very good, the very low noise floor. Meaning the dark counts and also the readout noise. These are the big performance booster. And of course, I mean small pixel size. Whenever you think about having high resolution images in the future, then of course you benefit from small pixels. Especially for the imaging with undetected light, it's actually very handy to work with the scientific sCMOS cameras that are out. It really is compared to other researchers or to the PhDs that work on the other fields, where you do not have the single photon stream for detection, but you have to consider the correlations and so on. It's much easier detection side. I mean, you already have cool systems, and one sees they developing further, and it's quite nice because you directly can live see the image that you're generating. You don't have to wait for it. You don't do much post-processing. You directly see live on the screen, and you put an object in your system, how it's generated. Then you can really do infrared imaging with visible light. And this works in live in video rate. This is really awesome, I have to say. Our very latest experiments we all did them with the scientific sCMOS cameras. And for example, one of the latest experiments was we actually established a new way of doing holography. It's called quantum holography with undetected light. So we actually thought about is it possible to combine quantum imaging with this undetected light scheme with classical techniques like, for example, phase shifting holography, and then get the benefits from both worlds together. And it turned out, yes, this is possible, and we could show this in the lab. And it was also a nice publication in Science Advances that we could place there. And this was, of course, possible with the help of a sCMOS, for scientific sCMOS camera. And we actually benefit from there because you have to take in a very short time interval 4 images, process them together to get the full phase and amplitude information out of your object. And this worked very well, and we're very happy about this. And at the moment we are now setting up on this knowledge, and now we are checking, for example, there are so-called quantum imaging distillation protocols. This means that if you have an imaging system, and there can be, for example, an additional light source that influence your performance of your detection scheme. Just imagine you want to image something, and there's an additional light source shining on your detector, and then if the additional light source is too bright, you will lose the information of your actual image. And then there are techniques to distill the image based on quantum properties. And we actually could show that in such a quantum imaging scheme with undetected light, you can do the distillation without using quantum properties, actually also with using classical approaches. This is based on the holography scheme. And we could really show that even if the additional light source is 1,000 times brighter than the actual image that you want to see, you can still retrieve the actual image by applying also this phase shifting algorithm on your system. And this was very nice to see. And again, it worked very nicely together with the sCMOS camera and was very reliable. This is one thing that we like a lot. You can just plug and play it. With the water cooler, you even reduce the noise floor further down. And then you can also do long-term experiments. You can run it overnight for some experiments. So this is all fine from our side. in the lab, we use as a scientific CMOS camera the Prime BSI from Teledyne Photometrics, and we are very happy with the performance, and it's a very reliable device. And yeah, we have actually more than one of those, and our latest experiments all relied on the performance of this camera. I would say actually that the foundations have been placed in the end of the 80s, beginning of the 90s. There you find beautiful papers from the Mandel group, from Leonard Mandel. You find nice papers from the Baltimore groups. That there was a lot of cool physics done. Also from in Florida, there are some groups that did a lot of pioneering work there. And I would say then there was like a small rally of forgetting all this knowledge. And then since, let's say, 2010, 2015, roughly, it started again that people thought, okay, now we have better technology, we have better ways of generating those photon pairs. Let's take out all those cool concepts that are already out, improve them a little bit, and bring them into application. And so both actually, so I said that the fundamentals have been placed very early already. Very still new physics, right? It's from the beginning of the 90s. But the big run actually started, let's say, 5 to 10 years ago to really bring those things into application, because then quantum physics turned to quantum technology, because now it's really a technological field, and now it starts to bring up real applications, and that people can benefit. People outside the research, the quantum physics research field. So I see myself as a researcher that I like fundamental research, but I also like, of course, applied research. Therefore, I'm also at the Fraunhofer Institute, and this is also the duty of the Fraunhofer Institute to do applied research. And therefore, I have the benefit actually to be able to cover both. Yeah, our research, it really takes the whole span. We have fundamental questions that we want to answer. Yeah, like for example, with this undetected light, which of the wavelengths actually is responsible for the final resolution of the image? This is already answered there, but there are more of this kind of questions which are on a very fundamental character. But on the other side, as I described, we also want to go to develop quantum microscopy systems at the end. Yeah, and I see that it's really going in this direction for the application side, that we can develop systems as new tools or additional tools for biomedical imaging. Yeah, because there in biomedical diagnostics, every source of information is important. Yeah, and if you have more tools available, this is always a beneficial thing. And therefore, we want to provide one new tool, which is then based on quantum physics, to get deeper insights into, for example, vibrational bonds of molecules, to identify and have some chemical selective imaging. And this is really the motivation that drives us forward. And from the camera side, what would be awesome, and what one already sees, is that the noise levels become lower and lower, and the efficiency become higher and higher. And what would be, like on my wish list, on the top priority list, would be if you at the end could really resolve per pixel how many photons impinging on this pixel. Yeah, if it's just one photon or have been 2 or 3. One sees that it goes in this direction. The development of the cameras is not there yet. Yeah, but people already try to figure out, okay, how many, let's say, photoelectrons are generated. Yeah, and then if one can make this more reliable, maybe then at the end one can also infer how many really photons hit this specific pixel. This would be a very cool camera, because then you would have photon number resolving, and with this you would have much more capabilities that you can use. Yeah, because then you can also think about new fundamental experiments, which then of course generate new applications, and so on and so forth.
Many thanks to Professor Markus Gräfe for taking the time to talk about his exciting work in quantum optics. At Teledyne, we understand the huge impact quantum technologies will have on the future, and we are able to commercialize academic research and move demonstrations to real-life applications thanks to our considerable capabilities. At Teledyne Photometrics, we lead and partner with a range of academic and industrial groups in order to industrialize quantum technologies. We are currently in a number of quantum dedicated partnerships, across Europe, as well as many other partnerships at institutions across the globe, all to facilitate quantum technologies and their use in imaging. But once you have quantum imaging solutions, it's important to be able to pair these with fast, sensitive, and large field of view cameras, particularly CMOS cameras. At Photometrics, this is our speciality. Our cameras are used in quantum research, either monitoring simulation systems or directly used with quantum imaging applications. The Kinetics and Prime family have been widely used in quantum research because of their sensitivity and speed across a big field of view. We also offer OEM solutions that can be easily adapted for custom requirements. If there isn't something that we currently offer, the capabilities at Teledyne mean we can realistically make a very wide range of camera technologies available for use in research. So our quantum imaging solutions that I'll talk about today are the Kinetics, the Prime BSI Express, and the 95B. The Kinetics is the next generation of sCMOS camera. It operates at extreme speeds across a very large sensor, all with high sensitivity. So with the Kinetics, there's no need to compromise. If you compare it with a typical 18mm CMOS camera, the Kinetics is 8 times faster with a 2.5 times larger sensor. So you get a tremendous amount of data. It also has sub-electron read noise. Because of all these specifications, it's become an ultimate solution for quantum. We have a number of people using them to image quantum simulation systems and even high-speed single molecule imaging of live samples. Because the field of view is so large, you can see here, if you compare it to an EMCCD in red or a typical CMOS in purple, the Kinetics, the large blue square on the outside, and the Kinetics 22, a smaller field of view version we offer, give you a vast amount of data and allows you to capture parts of your image that you just couldn't see before. This means it's higher throughput because there's more data in every frame. Because there's more data in every frame, you don't need to take as many pictures. So there's less tiling, less stitching, experiments are much faster, and you give your sample less light dose if you're working with photosensitive samples. You can also pair it with a splitter and split this massive field of view up to 4 times and image 4 quadrants simultaneously. We have people who image 4 different wavelengths simultaneously, 4 different fields of view, 4 different focal planes, even different polarizations. And if your microscope isn't as large as the full size of the Kinetics, we also offer the Kinetics 22, which is optimized for microscopes and systems that go up to 22mm maximum field of view. The other important aspect of the Kinetics is speed. It'll operate at 500 frames a second across this large 29mm field of view. If you reduce this to a 18mm field of view, it'll operate 8 times faster than standard CMOS cameras. And because this is a CMOS camera, every time you half the field of view, you double the speed. So you can establish extreme speeds of small regions of interest over 100,000 frames a second, or over 100 kilohertz. You can get the field of view that's just the right size for your sample and image it at the optimum high speed. This allows you to see what you were missing before in between images with a slower camera, and is only possible due to high sensitivity. If you can image at 1,000 frames a second, your exposure time has to be 1 millisecond. This means you need to be able to detect everything your sample has to offer within 1 millisecond of exposure. So you need a very high sensitivity camera. And as another bonus, this all happens in 8-bit mode. So your files are half the file size, which is helpful if you're taking many thousands of them at high speed. If we look at a typical CMOS, it would need to establish this kind of region to capture 500 frames a second. With the Kinetics, the full field of view captures 500 frames a second. So another way to look at this is that you get the same speed with an 11 times larger area. The field of view and the speed marry together beautifully. The other point to make here is the sensitivity. Quite a lot of quantum imaging applications work with extremely low signal levels. For a nice crisp image, you really require a high signal and a low noise. You want your signal to noise ratio to be as high as possible. Our Kinetics cameras offer 4 different modes, and you can push the read noise, and the speed in either direction. But in all of these modes, the signal collection peaks at a near-perfect 96% and stretches into the near-infrared, up to 1,000 nanometers as we saw before. The noise sources are all minimized, especially if you use our sub-electron mode, where noise is at sub-electron levels, 0.7 electrons read noise. With no patterns and no artifacts, kinetics cameras are highly sensitive because you've minimized the noise and you've maximized the signal collection. As an example of this, the Kinetics 22 is currently in use at the University of Munich Quantum Optics Group. They needed a large sensor and a high signal-to-noise ratio in the near-infrared region to image their optical lattices. Professor Monika Eidelsberger found the Kinetics 22 greatly improved upon previous imaging solutions because it has a great signal-to-noise ratio, small pixel at 6.5 micron, and a large sensor size. Here we can see an image taken by the Kinetics 22 of ultra-cold cesium atoms pinned into an optical lattice. This kind of application is widely used in quantum research, and the ability to image single molecules at high sensitivity is very valuable in order to characterize and test these systems. The next camera we're going to talk about is the BSI Express. This is also a high-speed and low-noise camera, and it comes in a very compact form factor. So you get 95% quantum efficiency, 95 frames a second, and 1 electron of read noise. This camera is really easy to integrate and is also widely used for lots of different quantum imaging applications. As a quick summary, the BSI Express is flexible, compact, and powerful. Its small size means that it's easily integrated into existing systems, and its USB for data means that it's also used in a lot of OEM devices. It's an ideal solution for many imaging applications, including quantum imaging. And if you do need higher speed, a larger sensor, or an even lower noise, the Kinetics series are available. But the Prime BSI Express enjoys a lot of use in quantum research fields. One such application is at the University of Twente Adaptive Quantum Optics Group, where they needed a fast-sensitive camera to observe photon Bose-Einstein condensate systems. Because the Prime BSI Express is highly flexible in software and hardware, it's the ideal camera for this application because of the low noise and high frame rate. The image here shows photon Bose-Einstein condensates, which are the bright spots on either side of the image, with the top image showing as the out-of-phase configuration, with 4 dots in between them, and the bottom image showing the in-phase configuration, with 5 dots between them. These Bose-Einstein condensate systems can be tuned like this, and it's important to have a camera that's sensitive enough to detect what phase your system is currently in, which the Prime BSI Express is doing nicely. Another application here is at the University of Berlin Integrated Quantum Photonics Lab, where they need to image low-signal tin vacancy nanostructures across a very large field. The Prime BSI Express has this large field and high sensitivity. And as Dr. Tim Schroeder says, with the Prime BSI on our custom setup, we can carry out experiments that we could not perform before. The image here is showing the bright spots of tin vacancy centers with an intensity scale across a large pixel map with high sensitivity. And lastly, from our speaker, Dr. Markus Gräfe, who's also using a Prime BSI Express at the Optical Quantum Technologies Group. They're developing quantum light sources in the NIR region with extremely low signal, and they're testing this with the Prime BSI Express, which is allowing the system to develop. Because it has smaller pixels than an EMCCD, it can give you a much better resolution, and you can make the system itself more compact because the camera is much smaller. This system has been used in a number of different studies and has been involved in a recent publication which involves quantum holography with undetected light. So I'd highly recommend everyone to check out Markus Gräfe's research as well. Finally, we have the third camera I'd like to talk about, the Prime 95B. The Prime 95B is the first back-illuminated CMOS camera, and it has very large 11 micron pixels. So it's designed to be very sensitive. It comes in a variety of fields of view. It captures our nice high peak 95% quantum efficiency. The Prime 95B has been a standout camera ever since it was developed in 2016 because it was the first camera to introduce back illumination to sCMOS cameras. With the large pixel and the low noise, it's highly sensitive. And we also offer additional advanced software features like Prime Enhance for increased signal-to-noise ratio, which is an active denoising system, and Prime Locate, which is a data reduction and live particle tracking, which we can see in the GIF here. It's in active use worldwide for a wide range of research and has been running on systems ever since it was developed in 2016. A great example here is Dr. Matthew Gebbie of the University of Madison Chemical and Biological Engineering Group, who is interrogating surfaces and materials with interferometry and optical spectroscopy. The Prime 95B is highly sensitive, and as Dr. Gebbie says, it's a uniquely powerful instrument. They didn't want to deal with EMCCDs. The 95B can continually push the limits with lower signal intensities at higher frame rates. As we can see here, the top image is interference fringes imaged with the 95B. The distance between some of these fringes is approaching the size of a water molecule. So it's really important not only to have high sensitivity, but high enough resolution to capture these. So in summary, these are our offerings for quantum research. We've got the flagpole, high sensitivity, big field of view, high speed kinetics. So our prime and kinetics families of cameras are highly capable. And if you'd like to know more, please reach out to us on our website. As a quick summary, here are the main specs for each camera. The point here is that we want to minimize read noise, maximize quantum efficiency, and give you a variety of different pixel sizes to capture the sample that you want to capture at the magnification you're going to use. With large pixel arrays, large fields of view, and high speeds, you can capture the information in order to answer the scientific questions that you have. So in summary, quantum imaging is a rapidly developing field with many practical applications of quantum phenomena. We can benefit pre-existing imaging systems, or we can even allow entirely new systems and concepts to develop. And I'm very excited to see where these areas go. These high sensitivity sCMOS cameras are vital for active development of quantum imaging research and also application of these quantum imaging solutions. So we have the prime family of cameras, but we also have the kinetics, where the motto is there's no need to compromise. Thank you very much for listening to this webinar. I would love to answer any questions that anyone has at the current time. Thank you again.
Thank you, Matthew and Markus, for your informative presentations. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the lower left corner of your screen. We'll answer as many of your questions as we have time for. All right. We have a question here that asks, is sCMOS the right technology for reducing read noise to 0 E negative?
That's a great question. Yeah, so, read noise is something that we'd like to reduce as low as possible. Because noise is error that you get when you read out the camera, you can definitely drive it to sub-electron levels. With EMCCDs, the relative read noise is around 0.2 electrons because you've multiplied your signal up so high above the noise. The noise is actually really high, but the relative noise is still only 0.2. And so I don't think you're ever going to reduce read noise to 0. I do think sCMOS cameras are going to be the technology going into the future, since CCD and EMCCD are not really able to keep up in terms of speed and field of view. So I think sCMOS cameras will definitely be the dominant technology going forward. They're already the dominant technology in a vast number of areas of scientific research. As far as reducing read noise, I think we'll get it really, really low. We're down to 0.7. You can get noise much lower if you're willing to sacrifice lots of other aspects of imaging. So if you're willing to take many images and then have the camera average them down, you can really reduce the noise. And this is what sub-electron mode is doing, is correlated multi-sampling. So if you completely sacrifice things like speed and field of view even further, then yes, you may be able to drive read noise all the way down. But in general, it's at the cost of other modes. I think noise will continue to reduce. But like I said in the presentation, now that the microelectronics are so small, they're being subject to quantum effects. So you can get cameras that work, in theory, perfectly. But the quantum effects within the electrons in these structures will move unpredictably and probabilistically, and you can't ever predict that you'd have a theoretically perfect noiseless camera, I think. I do think that denoising algorithms have come a long way, however, in case you want to reduce the noise in the post-processing step rather than live on the camera.
Fantastic, thank you. All right, looks like we have another question here. It says, do you think a photon counting sCMOS camera is within a few years horizon from Teledyne?
I think it's not unreasonable to expect something like that. We are moving to, most times you talk to people, they want a larger field of view so they can capture more data, or a higher speed so they can capture more data. And then the other field is, oh, I want to capture slightly less data. I want to refine the data I'm capturing. I don't want to capture the whole field. I just want to capture these 50 dots here. And so you can use these systems to try and capture only the data you want and not have to store it all. And other people want systems to capture as much data as physically possible. So the cameras are being refined for this kind of thing. For photon counting, you have to lean heavily into sensitivity and sacrifice a lot of the other factors. I think with something like the kinetics, you can see it's really fast and really big, and you can kind of push the speed and the read noise in different directions with its 4 modes. So I think that it will become more sensitive and more capable of photon counting, but I think it'll need to do all the other things as well. And so unless you want to make a product where you sort of sacrifice all the other performance just so it can do this one thing, then it might be possible. There's also a lot of movement within Teledyne's other sister units. We've got Princeton Instruments. They've got a lot of cameras that are very high sensitivity. You've got gated cameras, intensified CCDs, all this kind of thing. So yeah, I think it'll be an exciting few years for camera technologies, and especially in the quantum area as well, because this benefits things like light sources. If you can have quantum light sources, there are just benefits that you can have beyond those of regular light sources as well.
Great, thank you. Our next question that we have here asks, what would be your recommendation for a camera for quantum imaging of laser plasma, like IR imaging with visible light?
That's a good question. So if you wanted to image in the infrared, you could use a silicon visible light camera. That works, as you can see, quite well up to around 1,000. If you want to go beyond that, the other technology would be InGaAs. So InGaAs isn't silicon, you're using indium gallium arsenide, and it's essentially, you have a peak from around 700 to around 1900. So effectively, when CMOS drops off, InGaAs starts to pick up. So if you wanted to image really far into the infrared, you can definitely use an InGaAs camera. It's a different kind of technology, so the noise characteristics are a bit different, but our sister company, Princeton Instruments, has several InGaAs cameras under the banner of Nirvana. And this is great for imaging in the infrared. You can go all the way through like a mouse leg, for example. So if you wanted to sit quite far into the infrared and image at very high efficiency, InGaAs cameras are there. But eventually you should hopefully be able to image with infrared qualities while detecting visible light, as we demonstrated with the quantum imaging with undetected photons. So at the moment, if you're going to sit in the shortwave IR region, InGaAs is probably best for now. And then if you wanted to only use a silicon camera and occasionally peek into the infrared, then there are other capabilities to push that out a little bit. There are also coatings and deep depletions you can do, so CCDs and that kind of thing.
Thank you. And it looks like we have time for one more question here before we go. That question asks, can you realize optical gating with sCMOS cameras?
That's a good question. I don't think I'm equipped to answer that. I know that we have the PI Max series of optical gated cameras at Princeton Instruments. These cameras are sort of picosecond gating. I don't know if you can apply that to sCMOS technologies. I guess the best thing to do would be to contact someone at Princeton Instruments and ask them. If you email me after the program, you can also ask me again, and I'll be able to put you in contact with some people who will know more about that. But yeah, I think if it can be done and there's lots of realistic benefits to doing it, we have the capability to do it within Teledyne and would be able to produce such things. It's whether or not it can be done and how much of an audience there is for that kind of thing.
Excellent. Thank you again, Matthew, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Teledyne Photometrics, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by our speakers via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone. Goodbye.
Thank you.